All right, welcome. So in this video, we will work through the solution to a following non-homogeneous system of three linear equations. So actually, in the previous video, we looked at the homogeneous version of this system. So we had the left side was the same, and we had constants of 0 for each of the three equations. So let's see what happens if instead we have a top equation, x1 plus 3x2 plus 7x3 equals 4. Second equation is x2 plus 3x3 equals 5. And the third equation is minus 2x1 minus 4x2 minus 8x3 is equal to 2. And we want to find the solution to this system of three linear equations. So we set up the augmented matrix like so. We perform elementary row operations such as replacement to put this in reduced row echelon form. So I want to get a 0 down here. I multiply row 1 by 2 and add it to row 3. And that gives me a row equivalent matrix over here. And then I move to my next pivot and I want to get a 0 down here. So I multiply this row by minus 2 and add it to the row below. And now what we can see is this matrix is row echelon form. It's not reduced, but even in this form, I can see I've got a pivot column here. I have a second pivot column here. We still can reduce it further, but we have two columns, or this is the column relating to x3, which does not seem to have a pivot over here. But continuing this process and putting this into its reduced row echelon form, we have the following result. And so now, again, x1 is a basic variable, x2 is a basic variable because they have pivots. x3, however, does not have a pivot in its column. So now we've got x3 is a free variable. And then we can go ahead and express our solution set in the following vector form. So we could first of all solve for x1. So we would have minus 11, and then we would bring the minus 2x3 to the other side. It becomes a positive 2x3. I can solve for x2. I would have 5 minus 3x3, and then x3 is free. So I can write this as a sum of two vectors. First being the vector of constants. So I have a minus 11 is the constant in the first entry. My 5 is the constant in the equation for x2, and for x3 we put a 0 as a placeholder because there's no constant down here. And then we can add to that the free variable x3 times the vector 2 minus 3 1, and again these values come from the 2, the minus 3, and the 1 in our solution, which we then can write as a vector equation p plus t times v. So now this is parametric vector form. Rather than have x3 here, I use the variable t. So my vector p is this vector of constants. It's minus 11, 5, 0, and the vector v is 2, minus 3, 1. So here's the parametric vector form of this solution. And in fact, this vector v that we have over here is the same vector that appeared in the solution to the homogeneous equivalent of this linear system. So on the next slide, I want to compare the two systems, homogeneous, non-homogeneous, and their corresponding solutions. Okay, so to kind of summarize some of the results from the previous slides, we first looked at this homogeneous system of linear equations, and we were able to find the solution set to this system that we can write in vector form. So the solution to the homogeneous system was x was equal to x3 times the vector 2 minus 3, 1. So in other words, we had x is equal to t times v, where the vector v was this 2 minus 3, 1. And then we just looked at a very similar looking system of equations. The left side was entirely the same, so the coefficient matrix is the same, but now we have a non-homogeneous system. So on the right side, the top equation is equal to 4, the second equation is equal to 5, and the third equation is equal to 2. So this is a non-homogeneous system. And we found its solution on the previous slide that we could write in parametric form like so. So you can see that the two solutions, they have something in common, namely this term t times v. So the vector v is the same in both of these cases. So let's take a look at what the picture might look like. So this black line in the graph down below, this is corresponding to the solution set for the homogeneous system. So that's this system over here. So any scalar multiple of v is going to be a solution. The blue line above, this is now representing the solution to the non-homogeneous system. And the result is we take the homogeneous solution and we are going to shift it by p. So in other words, everything on the solution set for the homogeneous system, which was this line, we add the vector p to it. So here's some arbitrary solution, tv. Adding the vector v would be a translation of this over here. So we're translating the solutions. And so this p over here, it gets denoted with a p because we often call this a particular solution. And the v over here, we would call the homogeneous solution. So this tv term comes from the solution to the homogeneous solution. And to get the non-homogeneous solution, we translate the homogeneous solution in the direction of p. Okay, so let's finally generalize the connections that we've been observing between solution sets, the homogeneous and non-homogeneous systems that have the same coefficient matrix A. So on the one hand, we might have a non-homogeneous system, and we're going to assume we have a consistent non-homogeneous system. So at least one solution exists. So let's denote that solution as x is equal to p. So p is some fixed solution that we call a particular solution to the non-homogeneous system. And so let's say we know one possible solution to the non-homogeneous system. And we also know that the homogeneous solution, this has a solution which can be written as x is equal to t times the vector v. So we're going to call this the homogeneous solution. And so if I know at least one solution to the non-homogeneous system, and I know how to describe all possible solutions to the homogeneous system, then we can generate all possible solutions to the non-homogeneous system. So here we just have one of them. Again, we might have an infinite number of solutions. So the way that we could describe all possible solutions would be to take one possible particular solution and add onto it the homogeneous solution t times the vector v. So let's take a look at why this theorem seems plausible. So let's take a look at what this proof might look like. So we want to show, right, what we need to show is that if we know that p is a solution to the non-homogeneous piece and tv is a solution to the homogeneous piece, then p plus tv is going to be a solution to the non-homogeneous system. So let's plug p plus tv into the equation for x. So in place of x, I'm now going to plug in this vector p plus t times the vector v. And now we can use properties that we have discussed about matrix vector products. Namely, the distributive property says that this is equivalent to taking A times the vector P plus matrix A times the vector TV. And from this, we can again use what we know about AP. So we know that P is a particular solution. So in other words, when I plug x equals P into this equation, out comes B. So A times P, that's going to give me B. And then next, since TV is a homogeneous solution, I know when I plug this in for x, I should wind up with 0. So I get from the first term AP when I plug P in, I get B out. I get the non-homogeneous solution, and TV is the homogeneous solution. So when I plug this in for X, A times that should give me the 0 vector. So the vector B plus the 0 vector, recall, is going to give me just the vector B back. So now what we've seen is that when we plug X equals P plus TV in place of X into this equation, what we get out is the vector B. So therefore, P plus TV is a solution to the non-homogeneous system because out comes the vector B.